Welcome everyone. So this is our 106th live stream geometry. We have two other people here with me so far, and more will probably join later. And today I'm taking problems from a couple different contests. So some I'm taking from a Singapore team selection test. Some I'm taking from the IMOC, which was a contest in Taiwan. And the last two I took from Mathly. So that's a Vietnamese journal that we've been doing for a little while in the past couple sessions. So if you want to join me in the future, feel free to email me at mgreenvieta1@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. So here's the first problem that I'd like to do. So this is from Singapore team selection test. I'm not sure what year. So you have a triangle ABC, and E and F are the feet of the angle bisectors from B and C. All right. So we have this and this, and then this is E. This is F. And then we draw the circumcircle of ABC. I'm a little surprised it says PQ or minor arc AC. I wonder if they mean BC, but let's see. So AC is parallel to PQ, and BQ is parallel to EF. Okay, so first let's draw Q. So where's our parallel line to? So BQ is parallel to EF. Oh yeah, it would have to be AC then. This is point Q. And AC is parallel to PQ. So this would be P. And we want to show PA plus P, PA plus PB equals PC. This is an interesting problem. Okay, so let me hide some things because the lines are too long. So PQ is parallel to EF, and PQ is parallel to AC, and we're saying that PA plus PB equals PC. It almost feels a little like Ptolemy's theorem. Let's check that that's true. So PA is 1.84, PB is 6.47, PC is 8.31. So yeah, it's true. So what would happen if we use Ptolemy? PA times BC plus PC times BA equals PB times AC. All right. Yeah, this is pretty interesting. I wonder if we draw this point right here. Does DC equal AP? No. I wonder, let's try this. Take this length, and so CQ equals AP because these are parallel. And maybe that gives us some congruent triangles. So
Not the intersection
what?
of PC with the circle. Sorry, you remove the circle.
Do what with the circle?
Center at C with radius CQ.
Okay. And see where it intersects the circle. All right. So
Intersect. Not this point. Intersect at PC.
okay.
PC.
Oh, PC.
And we have to show PB equal PD.
Yeah. So then we have to show PD. PB equals PD. Yeah. All right. Let me turn my volume up just a little bit so I can hear you better. I'm just going to leave that circle there. See what happens if we draw this circle. Yeah, there's got to be some congruent triangles somewhere here. Oh, one sec, guys. I'll be right back. All right, thanks for waiting. Sorry about that. Let's see. So yeah, really we want to see if there's any like congruent triangles or something. Or what we could do is we could draw this and try to show that CG equals PB. Do these, maybe these angles add up to 90? Let's see. $32, 50.9. Yeah, the key is figuring out how to use that BQ is parallel to EF. That doesn't seem so easy. I don't know if it's worth trying the whole line EF and seeing where it meets the circle. Maybe we could use Ptolemy more than once. So let's see. Hey Pascal, thanks for joining. So this is our first problem. So yeah, you have a triangle ABC, E and F are the feet of the angle bisectors. And then you draw BQ parallel to EF, where Q's on the circle. And then you draw QP parallel to AC. And then we have to show PA plus PB equals PC. And PC is also equal to AQ. So PA plus PA and PC are QA and QC. So maybe that's an easier way to do it. I didn't even think about how PC is really QA. So we could even try using Ptolemy on ABQP. It's interesting. And then maybe we could combine those two equations. I kind of like that idea. So we have AP times BQ plus AB times PQ is PB times PC. And then, so yeah, I'll write out those two. Maybe that can help us. I wonder if EF passes through this point. I don't think it does, but let me check. So we have AP times BQ plus AB times PQ is equal to AQ is the same as PC, so that would be PC times PB. That's one equation. And then if we use Ptolemy on this other quadrilateral, we have AB times PC. AB times PC plus AP AB times PC plus AP times BC is equal to AC times PB. So can we somehow combine these two to get this equation? Maybe we could multiply this by PB and then, actually I don't know about that. I wonder what happens when I take PC and I replace it with PA plus PB here. See, it feels like this one's the easier one to work with because it doesn't have point Q in it. So if I did replace this here, it would be the same as saying that PA times AB plus BC is equal to, so I'm just replacing it right here. And then is equal to PB, so I'll subtract it from both sides, PB times AC minus AB. So if we can prove this, that's equivalent. It's kind of interesting. So really we need to show PA over PB is that ratio. AB plus BC over AC minus AB. I feel like projective geometry might help because, so here's the in-center. This is tricky. We have to use that BQ is parallel to EF. So I was thinking maybe we could project through B like EF and infinity, but I don't know what the other point would be. Maybe what I could do, if I let EF intersect BC, I think that might be helpful. So we could project like EFG infinity onto the circle. And then we get QA, and this would be the midpoint of arc AC, and then this would be C. But we eventually need to get something with these lengths. Probably trig bash some of it, because let's see, PA is equal to QC, and sine QBC over QC is sine BQC over BC, which is just sine BAC over BC. And this angle right here, I think we can calculate it. It's just this angle, which is B over 2 minus this angle. Oh, but I don't know if we can calculate this angle right here. PB is a little bit of a tricky length because we can't rewrite it in terms of something else. So PA and PC are QC and QA, but PB, I don't see an easy way to do that.
Are AB and PI parallel?
A, B, and what are the two?
AB and PI.
E or E I. Oh, A P and E I.
AB and PI.
Oh, A, B, and P, I. Sorry. Let's see.
Maybe not.
No. Yeah, let's see. Can we find a triangle congruent to PAB? Is CDF congruent to PAB? I don't think so, but no, CDF couldn't be congruent. Let's try something. Let's see. Yeah, how do we use that BQ is parallel to EF? That's really the key to this problem. I wonder what the tangent at A is. I wonder if HI is parallel to BC. I think I might have seen something like this before. Yes, I think that might be true. Yeah. Yeah, if we draw the tangent at A, the circle, and let it intersect EF at H, then HI is parallel to BC. So maybe that's helpful. And the proof of it, I think, is just like similar triangles a couple times. Because HIF would be C over 2, and HAF would be angle C. I'm not sure the whole proof right now, but I've seen that before. PB, how can we find that? All right, let's spend another maybe 10 minutes, and then we could try moving on to the next problem. I think it might be easier. Like for example, what if we did this instead? Do we want to show I want to try to get a triangle that's congruent to PAB. So if I do this, there's no way CE is equal to PB. Yeah, okay. So for example, one way to do it is, so PA equals PB, and so I want to show like CD equals PB, and then I could also draw this circle. And basically, oh no, because I need this to equal AB in order for these to be congruent. I didn't realize that. But I could do this. So this angle should equal this angle. So I could draw this point, and then I could draw this point, and then CJK should be congruent to PAB. Oh, and it almost looks like JK is parallel to BQ. Interesting. So that might be helpful. I don't know if that's obvious. Maybe an angle chase would prove that. I wonder if BP. So BP and BQ are isogonal. I didn't even realize that. So yeah, that would just come from the fact that BP and BQ are isogonal. That this would be parallel to that. So yeah, CJK is like congruent to PAB. Is BJ equal to BI? That would also be interesting. No. So yeah, maybe we could use the orthogonal line lemma. So like if we draw this point, and then we let PA and QC intersect, then those two would be orthogonal. I just don't know how much that would help. So yeah, if we let these intersect at a point really far away, sorry, I'm just gonna make it closer for the time being. So BL and this line should be orthogonal, but I don't see anything special about this line, so I don't know if that's really helpful. Oh, sorry, I'm sleepy today. I could also try flipping around this triangle. So basically, like CMD should be congruent to PAB. You could try using that. We'll delete K and L, K and J. Is that right? No, not CMD. It would be sorry. It would be this. It almost looks like point E, but it's not. It would be CM. CMN? Yeah. Well, that's interesting. These like concur, or it looks like they concur. Oh, but that's obvious because this is an angle bisector. So CMN. Is there anything special about N? Yeah, this problem seems hard to me. You guys want to move on? I think I'm gonna try a different one. Let's see. Let's try this one. So we have a triangle ABC and we have 3 Chevians. I don't really like the notation of this problem, but I'm going to go with it. So we have A naught, B naught, and C naught. So I actually don't think we need to draw all of them. I think we only need to draw B naught and C naught. Oh, actually, maybe we need to draw all of them. Let's see. Actually, let me try a different problem. This one looks a little ugly. This one might be a little easier. So yeah, let's do an easier one. So we have altitudes BE and CF, and then we draw the antipode of A. So A prime. So we have BE, CF. This is D. And then we draw DE and DF, and they intersect at Y and Z. First, I'll draw this diameter. So this is Y. This is Z. And Y, Z, E, F, and B, C, we want to show they concur. All right. So yeah, I think we've probably done this problem before, but I don't remember the solution. So let's see, Y, Z, E, F, and B, C. How do we want to do this? So it looks kind of like the radical axis theorem. In fact, it's equivalent to showing that Y, Z, E, F is cyclic. Because then we could use the radical axis theorem on these 3, and then that would prove it. So yeah, how do we show Y, Z, E, F is cyclic? Maybe power of a point from D. We'll just draw in the ortho-center H. This pass through another point. I don't see it. So we could show that dF times dz is dE times dy. That would solve the problem. I wonder, so AD and EF are actually perpendicular. So that might be useful. So this is a right angle. Okay, this is interesting. So these are cyclic. So AYGE and AZFG are cyclic. And I think that solves the problem, because if AZFG is cyclic, then BF times DZ equals DG times DA is DE times DY, which means that that's cyclic. Yeah, so this is an easy one. Okay. They're not all that hard. Yeah, some are easy. Yeah. Okay, so first of all, AD and EF are perpendicular because if you look at the angle that EF makes with BC, I'm trying to think about the best way to do this. So AO and AH are isogonal. So yeah, I'll just write it like this. So BFEC is cyclic. And AH and AO are isogonal. That means that AD is perpendicular to EF. So let AD meet EF at G. Then AZF is 90. So AZF is AZB is 90. Which is AGF. And that means that AZFG is cyclic. And then similarly, AYEG is cyclic. AYEG is cyclic. So then by power of a point, dF times dz is equal to dg times dA, which is equal to dE times dy. So that means FZYE is cyclic. And then we can use the radical axis theorem. So by the radical axis theorem on FZYE, BFEC, and ABC, then that solves the problem. YZ, EF, and BC concur. So that is a little bit of an easier one. All right, let's just draw on those circles. This one and this one. All right. Let's move to another problem. This one's kind of interesting. So you have a bicentric quadrilateral. So I think there's a general way to construct them. So basically, we have a quadrilateral that has both an in-center and a circumcenter. So it's both cyclic and it's like circumscribed. So I think what you could do to make them, all you have to do is you draw two perpendicular chords, and then you draw the tangents at those points. I think this is like a well-known way to construct them in general. So if I draw the four tangents at these points, then it should make a cyclic quadrilateral. So let's see how it works. Yeah, I don't want to make it look symmetric, so let's try this. So yeah, I think these 4 points should be cyclic. And I think this is in general how you construct it. Yes. Okay. So ABCD should be the quadrilateral. EFGH should be the points of tangency. So A, B, C, and this is D. And then it says in counterclockwise order. So let's say E, whoops, not A, E, F, G, H, and then let O be the center of that. And we draw OEG and OFH. That's interesting. OEG, whoops, OFH. Draw those two centers. And we want to show it's perpendicular to OI. So I doubt OFH. We want the center of that circle. Okay. So OI we want to show is perpendicular to JK. All right. 1, 2, 3, 4. Yeah, I don't even know if we really need to draw those two, but it's true that they're perpendicular. That's true. I forgot the proof, but whenever you have a quadrilateral, it's called bicentric. It has both an in-center and it's cyclic. That's true. Okay. Interesting. Sorry, I'll be right back again. All right, I am back. Yeah, this is a really weird problem. It's the same as saying that JK is parallel to the radical axis of these two circles, right? So I guess another way to say it is the same as saying that OL. It's the same as saying OL and I are collinear, right? So I think that's an easier way to think about it. All right, looks like Khan is joining. Hey Khan, good to see you. Thanks for joining. Yeah, hey, thanks for joining. Good to see you. So yeah, this is our second or third problem. Hello. So yeah, this problem, we have a bicentric quadrilateral, ABCD. So it's cyclic and it has an in-center at the same time. We draw the circumcircles of OEG and OFH, and we let J and K be the centers, and we want to show JK is perpendicular to OI. And I realize that's the same as showing that OI and L are collinear, where L is the intersection of those circles. I wonder if L lies on the radical axis of these two circles. I don't think that's true. How do you draw the radical axis of two circles? Is there an easy way to do it? I guess if we want, we could check by drawing tangents. No, it's not on the radical axis. Maybe it is. Now I'm starting to think it is. I think I just didn't draw a good picture. So let's see, if you zoom in, it sure looks like it. Let me move things around a little bit before I'm sure of that. No, it's not. Because this is the tangent to this circle, and the length isn't the same. Okay. So yeah, L's not on the radical axis necessarily. And yeah, it's well known, I was saying, Con, that GE is perpendicular to HF. I wonder if the intersection of those also lies in the, yeah, and the intersection of those I think also lies in the diagonal. K I don't think lies on that diagonal, even though it looks like it. Yeah. Maybe, I wonder if this intersection point lies on the line OIML. Yes. So that could be very useful. I don't know why that's true, but it looks like it's probably useful in solving the problem. So maybe we could show OI and M are collinear. I think that's a well-known theorem, isn't it? That OI and M are collinear. I don't remember the proof of it though. Let me see, it's probably on Wikipedia, I would guess. Let's see. I don't even see hmm. Yeah, so this idea that these are collinear, first of all, the idea that the idea that G, M, and E are collinear and H, M, and F are collinear. I forget the proof of that, but is that even true in general? Is IK perpendicular to JI? I don't think that would be true, but let me check. Because, oh, you're right. I don't know why. Yeah, IK is perpendicular to JI. It's my bad. Interesting. And we want to show JK is perpendicular to OI. So But yeah, like the picture I'm looking at on Wikipedia almost makes it look like B, M, and V are not linear, but this makes it look like they are. I think that might just be a weird picture. Yeah, so it says on Wikipedia, O, I, and M are collinear. That's like a well-known property. And we could try to prove it if we want. But yeah, there's a proof of it on cutttheknot.org. So O, I, and M, it's kind of well known they're collinear. And then to show those are collinear with L, I don't know why that's true yet. So maybe we could show O, M, and L are collinear. So that's the same as saying that we want to show that M lies on the radical axis of these two circles, right? If we show that, so the power of M with respect to this circle is MH times MF. Oh, that's true, it does, because MH times MF is MG times ME. So M has the same power with respect to these circles. So O, M, and L are collinear. And then the well-known fact says that O, I, and M are collinear, and so that would solve the problem. But I don't know why the well-known fact is true. So do you want to try to figure that out? Yeah, so so it's well known that GE HF BB and AC concur at a point M. And then since mg times me equals mh times mf, that means that M lies on the radical axis of OGE and OHF. And that means that OI and L are collinear. Sorry, OM and L are collinear. And then it's well known that OI and M are collinear. So so that means that OI and L are collinear. All right. Hey, Chuan, thanks for joining. Good to see you. And that implies JK is perpendicular to OI. So, or I'll just say, yeah, perpendicular to OI, and that implies what we want to prove. Let me just copy and paste it. So. What? Why is it not working? All right, I'm gonna try it one more time, and then if it doesn't work, I will probably just give up and type it out. How do I copy it? Copy, Control C, and it's not gonna work. Okay, so I'll just type it out. The circumcenters of OEG and OFH is perpendicular to OI. But yeah, the question is, can we prove that well-known fact that OI and M are collinear? Is it obvious? And this fact too, but
I think I have found a way.
okay.
Okay, by Brocard theorem on the incircle and the circumcircle.
Okay. So should I extend BC and AD and AB and CD?
By Brocard on ABCD, we get OM perpendicular to like a line.
OM is perpendicular to what? Oh, the two intersection points. Yeah.
Yeah.
Okay.
By Brocard on the incircle, like we have OI perpendicular to that line.
Oh.
Two times.
Okay, so yeah, we use Brocard's theorem. So OI is perpendicular to the line connecting these two intersection points, and then we use it on the incircle. You said.
Yeah, because like draw the intersection of the extended points,
Okay.
BC and AD.
Yeah. So yeah, basically you're connecting these, right?
Yeah. So HF passes through the.
Oh, HF passes through this point? Let's see.
Yeah, yes.
Really?
This is Newton's theorem or something.
Wait, HF doesn't pass through this point.
Why?
Or the picture doesn't show it does.
Oops, wait. Wait a minute.
But I see you're saying OI is perpendicular to NP. Or, sorry, OM is perpendicular to NP. And IM, okay. So basically, I think EH and GF meet on that. That's the idea. So EF and GH meet on that, and GH and EF also, I think, meet on that. So why is that? Is that just what?
Pascal.
Pascal's theorem. I thought it might be Pascal's. Okay. So this is interesting. Let me see mechanism for all this stuff. So
Right.
okay. So hide this, hide this, hide this. Okay. So we have this and this. They meet on it by Pascal's theorem. I'm not going to draw the other one. It's too far away. But so I'll say prove star. Label the points as shown. Whoops. And then by Brocard's theorem, OI, by Brocard's theorem on ABCD, OM is perpendicular to PN. And then also by Brocard's theorem on the inner circle, so E, F, G, H. Okay, so I'll say by Pascal's theorem, Q lies on Q equals Q, and I'll say EF intersect GH equals R, not shown, Y on PN. And then also by Brocard's theorem, IM is perpendicular to QR. IM is perpendicular to PN, and that implies OI and M are collinear. All right, I like this. This is fun. Okay, so
one question.
Yes.
How do you know OIL are collinear?
How do I know OI and L are collinear?
Yes.
Because, hold on 1 second. Because, so OM and L are collinear by this, and OI and L are collinear. Sorry, there should be M. OI and M are collinear. So by this, well, in fact, OI and M are collinear, and by this fact, OM and L are collinear. So if you combine those two, then OI and L will have to be collinear.
OML are collinear. Oh, by power of point. Okay.
Yeah. So yeah, because mg times me is mh times mf, so it has the same power with respect to these two circles, so it has to be on the radical axis. So yeah, this is a good problem. All right, so.
But I have a confusion. Like we don't know. Like it lies on MO.
We don't know. Yeah, we don't know L lies on MO, but we don't have to know that to do that because, sorry, let me try to max. It won't let me maximize this, but basically, if we can prove, we know that G, M, and E are collinear, Well, that's a well-known fact. I didn't prove that. But G, M, and E are collinear, and H, M, and F are collinear. And so we can prove, like if I hide this line for a sec, HM times MF is GM times ME. And so that means M has the same power with respect to these.
Yes, that makes sense.
Yeah. All right. So thanks.
Okay.
So I'll move on to. So this problem we actually tried before, but we can